okay? In the past, much less was possible. And this lot that gets done, you know, should go to benefit people. So I'm not criticizing the modern world just because I'm an old man. I think that we always go towards better things, that the past is not better than the future. So, but still, some things need time. That was true in the past, and it is true also today. I see it with my many students and so on, collaborators, okay? And so don't worry, okay, about what is happening in these classes in such a short time. Of course, if you have questions, just get back to me. And in the tutorial hours, that we have 2 tutorial hours also today, maybe there is a chance to discuss things more. Now, the amount of material I would like to cover this morning is not too much, so maybe we have time for some exercise that then you implement in the tutorial hours, okay? We'll see. We do what is possible to do. And what is not possible is not possible. Okay, so I start now. We had 6 academic minutes. I don't know, maybe other people are coming, but perhaps I should start, right? So if they come, in any case, there is the material. It is all in print, what we use, what we do today. Yeah, unless there are questions directly that I can try to answer before I start today's class. Or if questions come along, you just stop me and say, okay? Okay, so let me go back to where we stopped yesterday, which was this, the definition of the evolution of a probability measure, okay? So we said that if mu is a probability measure, maybe this probability depends on a time t. And this probability measure can be used in various ways. One is to attribute a weight to subsets of the big space, which is called phase space. Okay? And that we define it as we would do with the mass of a fluid. Now, if you keep this in mind, it will help you to see through the calculations, because some calculations get a bit involved. But you keep in mind this, if it helps you, okay, if you have physical intuition about a fluid. A fluid, for instance, a gas, the air in this room, okay? Yesterday I spoke about the water that goes from the glass into my stomach. Okay, it's the same thing. When the winds blow, air moves around, okay? And it carries with itself its own weight. Yes, air is thin. It's not very heavy, but it has a weight, okay? It has a mass. It has a mass. The weight comes from the force of gravity, but the mass is a property of the molecules of air. So when they move around, maybe they get compressed because there is high pressure, and then you feel hot, okay? Or maybe they expand because there is low pressure. So the volumes can change, but the mass remains the same. The volumes can change and can move from place to place. Okay? Now the winds are blowing in Delhi, hopefully. They're not blowing here. But the perturbation may move. Okay? It comes here. So the mass has moved. It has changed shape, but the mass remains the same. This is the idea. Okay? This is the idea. We think that probability is like mass. And mass at time t in a location E is the mass that at time 0 was in the pre-image. Okay? This is the meaning of this abstract formulation, but in the end, it makes sense. Why do mathematicians develop such a formula? Well, because whether they want or they don't want, they think about the real world. Sometimes you hear that mathematics is a beautiful abstract thing. Well, okay, it is an opinion. Okay? I think that it is that to be totally abstract is impossible, because we are made of flesh. We touch things with our hands, and these are the only things that we know. Nothing comes out of nothing. This is an old saying of the Latins, okay? Ex nihil nihilo. Nothing from nothing. So we always have something in mind. And in fact, mathematicians give names to these things. Okay? And you will find that this is called mass in mathematical textbooks. But if it is the probability of temperature, certainly there is no mass, right? But we call it mass because that helps our intuition. So this is the meaning of the formula. Keeping that in mind, maybe that calculations look more reasonable. Okay, so this will be equal, by definition, to the integral over the set E of the probability at time t. And this will be equal to the integral over the set phi minus t E of the other probability, d mu 0. Okay? Now, we introduced the characteristic function that is 1 when you are inside E and 0 when you are outside. So you can write this in a more general form, which is integral over the whole phase space. So this can change, this does not change. Over the whole phase space of a given function, chi E, the characteristic function, evaluated, and this will be the integral over the whole M. You see, it's the same. Of what? Of chi, the characteristic function. Now, this is based on phi minus t E of x, and this is d mu 0 of x. Okay? So these are things that you can use. Now, suppose that you are not, then when you do an integration like this, you have a function and a probability. What you obtain by definition is an expectation value, is an expected value. So we can write this also as expectation. Now you see the difference between E, a subset, and this thick E is expectation, okay, at time t, of my function chi E. This is the definition of expectation, is the integral of my function with respect to this measure. Well, you may wonder, why do I call it E? It's not me. It is probabilistic terminology. It means event. That is the probability of an event. Which event? The event of x being inside E. Okay? It is an event. What is the probability that temperature is between, today, I don't know, it feels around 10 degrees, something like that, 8 degrees. What is the probability that it is between 8 and 10? Okay, the event E, in that case, E, would be the set 8, 10. Okay, and M will be, if we want to exaggerate, the real numbers, assuming that temperatures can go from minus infinity to plus infinity. Luckily, it doesn't happen. But in some places in India, it seems that the upper bound doesn't exist. Being in the south, in some pretty hot places, even in winter. Okay, so also this helps. Now, if you integrate your function, whatever function, a function in a given function space, often we take L1. Okay? Although it is a huge space. You get the expectation value. So here you have the expectation value at time 0, because the probability is the probability of time 0, of a different function, chi phi minus t e. Okay? Now take a more generic quantity, observable as we called it, okay? We call it O. And O is just a function in our function space that goes from the phase space to the real numbers. Okay? Now we can take the expectation at time t of observable O. By definition, it will be the same thing. It will be the integral over m of O of x d mu t of x. Okay? And as we did that, we could have taken the expectation at time 0 of the same observable O. You see, there is a difference between this and this. This is an expectation at time 0, okay. This is expectation at time t, okay. So like here, at time t and at time 0, but of two different functions, chi e and chi phi minus t e. Okay? Here I'm taking the same function. So in general, these two are different. Okay? They are not the same. Now, you understand the sequence of equalities that I have written on top? They correspond to the fact that the mass is conserved. So we are saying the probability is conserved, even if it moves around. That is the meaning of this sequence of equality. But if I look at the expectation value of temperature today and of temperature tomorrow, they will be different in general. Okay? So you don't have that sequence of equality. So if you have the same function, but you change the probability, then the expectation may be different. It doesn't always happen. Okay? It doesn't always happen. It may happen. You see the eraser? On the other one? By the way, Sivaraji, these markers are very nice. Yeah, right. They're good. They're good. So it could happen. It could happen that the expectation remains the same. Et of O is equal to E0 of O. If, okay, if this is true for every observable in our function space, let me call it F. If it is true for every t, say, could be real, but could be integer, like in the case of the logistic map. Okay? If it is true for every observable in the space that you have chosen, and for every time t, then okay, it is true also for the characteristic functions of the sets. Okay? Then what you have is that E0 of chi e, by definition, is equal to Et of chi e. Sorry, by definition. I mean, by the hypothesis. Because chi e is a function. It belongs to the space. Okay? But by definition, Et chi e is equal to E0. You see? Go back, is equal to E0 chi phi minus t e. So now you have this equality. Okay? If it so happens, okay, which I told you is not true in general it will not happen. But if it does, then you have that the expectation of the characteristic function chi e. But what is that? That is mu0 of e. Okay? Expectation of whatever time. Chi e is its measure, its probability. So this is equal to this. And this is equal to its to the measure of phi minus t e. Okay? But mu0 of phi minus t e is equal to mu t of e, which is here. So you know what happens? That the probability of E does not change. So if expectations don't change, probabilities don't change. And it is two-way. Of course, if the probability has not changed, the expectation will not change, because you do the same integral. Okay? If the probability here is the same probability that you have an earlier time, okay? If the probability here is the same that you have here, this integral and this integral are equal, because the function is the same. But it goes also the other way. If expectations are the same, don't change in time, then probabilities must be the same, provided this equality holds for all observables. And all observables means for all subsets of the sigma algebra that you have chosen. Okay? So things go this way. They can go both ways. There is one that is more mathematical way, and there is another one that is more physical, if you like. The physicist will like to look at the observables, because they are the things that you can measure with measurement tools, with a thermometer. Okay, so they will choose the function space. They will tell you what are the quantities that they want to measure, which means the quantities of which you want to compute the expectation. And mathematicians are open to all possibilities, but they will not dislike the idea of looking at the probability of the event rather than at the expectation values. Okay? But the two things are perfectly parallel. I choose a sigma algebra, which is a set of events of interest, or I choose a function space. You see in this sequence of equalities that can be connected to each other. Also because the characteristic functions, linear combinations of characteristic functions that are called simple functions, are dense in the space that you have. Okay? So it is very much entangled. You choose what? You choose what? Even mathematicians, however, will agree, and we see in a moment, that it is still better to work with expectations than straight with probabilities of events. Okay? Because events can be, even if you have chosen a mild sigma algebra, they can be quite ugly to look at, okay? Like fractal sets, or quite beautiful. That depends. But if you plot them on a computer, you can see beautiful pictures coming out of fractals. If you have to do calculations with fractals, it can be quite complex. And of course, some of our friends are very much experts of fractals, right? Here also. So far from me saying that they are ugly, it was just a way of saying, you know, it's a complex object to deal with, not very simple. Expectations are simpler. Expectations are simpler because they are the result of